So the first question, 3A, xenon tetrafluoride SEF4 can be used to help find and analyze trace metals that contaminate silicon rubber. So first, draw the Lewis structure for XeF4. So for Xe, 1 Xe times 8 valence electron equal to 8. We have 4 fluoride. So 4 times 7 valence electron equal to 28. So total electrons is 36. So first, Xe will become our central atom because the number of Xe is less than F. We have 4 fluoride, but we just have 1 X xenon. So Xe will become our central atom. First, the Xe will form the bond with F. So Xe will form 4 bonds with 4F. 1, 2, 3, 4. So each bond have 2 electrons. So we have 4 bonds. 4 times 2 equal to 8. So the 36 minus 8 equal to 28. Next, we want to add the electrons on F to the terminal atom first. So F we already have 2 electrons here. So we need more 6 electrons to achieve the stable octet. So now here F, I add 2 here, 2 electron here, and 2 electron here. So total is 6. So these 4 fluoride, all we add 6 electron on it. So 6 electrons times 4 fluoride equal to 24. So we remains 4 electron. So the 4 electrons we will add to the central atoms, which is Xe. So we have here 2, here 2. So 4. So minus 4 equal to 0. So this is our Lewis structure. Next, based on VSEPR theory, predict the electron pair arrangement, molecular geometry, and bond angle of XeF4. So first, we want to know about the class of compound. The class of compound is AB4E2. Why? Because it has bonding pair 4 bonding pair here. And for central atom have number of lone pair is 2. 1, 2. So dotted up we have 6 electron pair. So the electron pair arrangement for 6 electron pair is octahedral. And then the molecular geometry is square planar because we have 4 bonding pair and 2 lone pair. The bond angle between the fluoride is 90 degrees here. Then we want to explain the polarity of XeF4. XeF4 is non-polar molecule. Bond dipole for XeF4 can cancel out each other, or you can say mu equal to 0. Why? Because you can see here lone pair, downward also lone pair. So the lone pair and lone pair can cancel out each other. And then the bond dipole is toward more electronegative. So more electronegative atom is fluoride. So it's towards fluorine. So here towards fluorine, here towards fluorine. So these 2 bonds can cancel out each other, and then this and this can also cancel out each other. So it's non-polar molecule. Next, describe the hybridization process of the central atom of XeF4 by using the orbital diagram. Okay, so first we need to know the type of hybridization for central atom first. So the total number of electron pair is sigma plus lone pair. So the sigma bond here, you can see here, Xe can form 1, 2, 3, 4. 4 sigma bond. So 4 sigma bond, 2 lone pair, 1, 2 lone pair. So 4 plus 2 is 6. So the type of hybridization is sp3d2. So first is ground state of Xe. Xe have 8 valence electron. So if you fill out 2 electrons on 5 5x and 6N 5p. And then we have 5d is empty orbital. Next we move on to excited state. For excited state, you can see the electrons on the 5p, 1, 2, these two is excited to the 5d. Excited. This is due to we want to form 4 sigma bond, so we need 4 single electrons. So you can see when it excited, we have 1, 2, 3, 4 single electron, and then we have 2 lone pair, so 1, 2 lone pair. So this is excited state. Then next is hybrid state. For hybrid state, sigma bond and lone pair will undergo the hybridization. So sigma bond and lone pair, so these 2 lone pair and 4 sigma bond. So you form this combine together and form the sp3d2, which we already find at upper type of hybridization. So we have remains 5d empty orbitals, 3 orientation is empty. B. Boron hydrate, BH3 and ammonia NH3 react in the ratio 1:1 to form a product. Draw the structure of the product form. So we need to draw the structure. So first we need to draw the Lewis structure for BH3 and NH3 first. Okay, for BH3, B have 3 valence electron, H has 1, but we have 3 H. So 1B will form 3 bonding pair with 3 H. So this is a Lewis structure. And then for NH3, N has 5 valence electron, H has 1. Okay, we also got 3 H hydrogen. Nitrogen will form the 3 bond with 3 hydrogen, and then it remains 2 valence electron, so it will form the lone pair of nitrogen. Okay, the nitrogen have lone pair here, and the B have empty orbital here, so nitrogen can share the lone pair with B, and B can receive because it has empty orbital. So one share, one no share, we will form dative bond. So now we calculate for the formal charge. For H, the 6 of these H are same, so I just count for one time. So the valence electron is 1 minus no lone pair, 1/2, 2 bonding electrons. So 1 minus 1 equal to 0. For N, nitrogen, 5 valence electrons minus also no lone pair. You see the diagram in here, not here, because we want to find the formal charge of product. So now N does not have the lone pair, and then plus 1/2 bonding pair with a 4 bonding pair. 1, 2, 3, 4. 4 bonding pair. So 4 times 2, 8 electrons. So 5 minus 4 is positive 1. For B, we have 3 valence electron minus also no lone pair plus 1/2, 6. This because the bonding pair of B is just 1, 2, 3. This bonding pair is for N. It just receive the B does not form this bond, so it just form 3 bond with 3 H. So the bonding pair electrons is 6. So 3 minus 3, 0. So total formal charge, we have 6 H, right? So add all the formal charge, plus 1 is nitrogen. Nitrogen is plus 1, so the total formal charge is plus 1. Okay, next. Name the bond formed in BH3 and between BH3 and NH3. So in BH3, here, we already say it form covalent bond. And between BH3 and NH3 is this, the arrow. The arrow one is dative bond. Next, compare the boiling point of BH3 to NH3. Explain the difference. Boiling point of NH3 is higher than BH3. NH3 can form hydrogen bond, but BH3 cannot. It just can form the weak van der Waals force. So more energy is required to break the hydrogen bond in the NH3. So NH3 has a higher boiling point than BH3. Okay, next. Aluminium metals is a good electrical conductor. Explain the electrical conductivity of aluminium using the band theory. So first, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. The valence band of Al is made up of 3s2, 3p1. Valence band is made up of valence electron. So the valence electron of Al is these two, so 3s2, 3p1. The empty 3p orbitals form conduction band. Conduction band is made up of empty orbitals, so 3p is only filled with one electron, so it's empty. Empty 3p orbitals will form the conduction band. So the valence band and conduction band is overlap because here 3p. The valence band also 3p, so they are overlap. So the electrons can move from valence band to conduction band. They can move. So when the electron can move, so the aluminium can conduct electric.